How time flies. It's been almost a decade since we heard the incredible announcement from the Breakthrough Starshot Foundation that they were funding the development of an interstellar mission, something that could send a spacecraft from the Earth to Proxima Centauri at relativistic speeds, 10, 20% the speed of light, and complete the mission within a human lifetime using lightsails, where you would fire a laser at a lightsail material that would accelerate it up to relativistic speeds, and you would be off to another star system. It's been almost a decade, and how are things going? Well, there have been incredible advances across a lot of the different technologies that would be required to make this mission a reality. More powerful lasers, better solar sail materials, and even more miniaturization of electronics to make this mission possible. One of the key parts, though, is the sail material itself. How can you have a sail that could be many meters across and yet still weigh about a gram and be able to handle the enormous amount of energy coming from a high-powered laser to be able to make this acceleration work? It sounds like science fiction, and yet people are continuing to make really interesting progress. My guest today is Lucas Norder. He is a PhD candidate at the Delft University of Technology. He and his colleagues have a recent paper called Pentagonal Photonic Crystal Mirrors, Scalable Lightsails with Enhanced Acceleration via Neural Topology Optimization, where they look into ways to make the solar sail material much lighter by punching holes in it, but the holes match the specific wavelength of the laser light they're looking to catch. And so by doing this, they can make a material that is lightweight and is able to still be accelerated by a solar sail. And they've been able to manufacture it relatively quickly at fairly large sizes. And now they're moving into testing, where they're going to fire a laser at this material and find out what happens. It's a fascinating conversation about practical engineering solutions to some of the challenges posed by the Breakthrough Starshot Foundation. Enjoy the interview with Lucas Norder. Lucas, it's been about 10 years since we first heard the big plans from the Breakthrough Starshot Foundation about sending a spacecraft to another star system at relativistic speeds within a human lifetime. How's that coming?
I actually think there's been a lot of progress lately. I think in the last few years, we've seen that the technology has developed to a point where we can finally put stuff in the lab and start to really see what the actual limits are that are out there. So we're now at the point where we go from theory to practice and actually start to see what are all the different constraints we have to take into account.
And specifically, I reached out to you because you recently had a paper in Nature. I mean, when these plans were first announced, the state of that technology, especially the sail itself, how are you going to actually have a laser sail that's able to transfer that momentum? And a lot of these were big question marks, unknowns. And so now you're saying that in fact a lot of this technological progress has been moving forward at a pretty good pace.
Yeah, I think so. So in 2016, when the Starshot Breakthrough was announced, a professor on which I work, Richard Norder, was working on nanophotonics. And nanophotonics is the field where you try to manipulate light with nanostructures. And what he actually saw is that the same requirements that you need to make these nanostructures for are the same requirements you need to have for these light sails. So if you want to make really sensitive measurement systems that do not heat up with light, you need to have certain materials that do not heat up and can actually withstand these powers. Same for these light sail materials. You put this big sheet of metal in space, you want to illuminate it with this huge ass laser, and the last thing you want to do is that it starts to explode, right? So we sort of saw these two things as like, oh, this is actually the same technology we have to develop. The only downside is we're now talking about nano stuff, and now we have to scale up these nano things. And I think that this is exactly where we in the last years, and we as a group as well, really try to push ourselves to see like, okay, what are the limits of these nanostructures, and how large can we actually make them? And this is exactly where we now where I can say that we started from things which are nanometers, millimeters, and now centimeter scale, and we've developed a way where we can even scale it up as well.
So give us a sense, like if you could look at one of these surfaces in the most powerful microscope on Earth, what would they look like?
Yeah, that's a really interesting question. If you look at them, you have like it's just like small ones. So in a traditional way, I think it's interesting to first look at how a traditional mirror would look like. Because a traditional mirror, you have one piece of metal, which you polish highly, put a piece of glass on it, and then you can reflect your light. But we need to have something which is really light, really lightweight, because otherwise the force of the laser wouldn't do anything. And then we have a special method to actually make this really thin, like 200 nanometers thick sheet, even more reflective. And what we do is we actually punch a bunch of holes in it. And that's a bit counterintuitive. Like you have this sheet of material, you put a bunch of holes in it, and that makes it more reflective. But what we actually do is we tune these holes to the specific wavelength of the laser which would come in. And it's the same thing as a string, as a guitar. The moment you tune your string to the certain sounds that you want to make. So we tune our holes to the wavelength that's coming in.
And sorry, and so I just want to understand this. And so are you trying to only let, you're trying to let other wavelengths through, but have it impact or hit the sail and not be able to pass through with the wavelengths that you want for the laser?
That's exactly what it is. We're actually making resonance with the light in our sail. And that's why the whole way of these light sails actually work is fundamentally different than how the traditional sails work. And that's actually really cool, because then you have these, for example, for our thing, which was centimeter size, you have it covered with billions and billions of holes, and then the light comes in, and then it interacts with the light that comes in, so it actually adds up, so you get a lot of reflected light, and it cancels all the light at the bottom. So this way, because you have this resonance with all these holes, you actually get extremely high reflectivities, and you get the added bonus of a reduced mass because you have all these you punched all these holes in it. If you take your if you go to an electron microscope, you would zoom in, you actually see a really nice array of circular holes. And for our specific wavelength that we use, they're around like 800 nanometers in diameter. And then I think what we showed in the paper is that where you usually tune it for one specific wavelength, we found a way with our optimization that we employed that you can also tune them to have multiple peaks. In this case, we had like two distinct peaks that we saw. And then you don't have these holes anymore. And I call it a pentagonal lattice because it's the shape of a pentagon, but mainly people call them beans or even speckles of a cow because it really looks like something else that we're actually used to, like more of an organic structure.
And so, this shape, is this due to what is the most effective laser light, or is this from a manufacturing side, what is the most straightforward to be able to build?
Yeah, that's a really good question. So, what the reason why we came to these shapes is that a lot of people were focusing on we need to make something highly reflective, but then you put your laser on it, and then you accelerate something. But what you actually see is that because you accelerate your sail, the light that the sail sees Doppler shifts. So the sail sees a different frequency, and now it's often in games that you tune it for one specific wavelength. But if your reflectivity drops, the amount of force that the light hits it changes. So there's so on one side you have the reflectivity over the whole region that the light will actually see, and on the other side you have the actually manufacturing constraints coming in. And here's this really interesting interplay, because you can get a lot of reflectivity if you have really small features. So if you have big holes next to each other and the distance between these holes is really small. But that's exactly where the manufacturing gets expensive. We have really advanced nanofabrication methods, for example, electron beam lithography, where you can go on nanometer features, but that takes hours, days to only illuminate a patch of centimeters. But if you go to a more straightforward method, which is like optical lithography, And here you don't go electron per electron, but you take a picture and you just in one go you can illuminate that picture. Then you can drastically increase your writing time and speed. But the downside of these methods, it's faster, but you need to have larger features. And this is where this interplay came, where we say, okay, we want to have a light sail, which is reflective of a larger region, but we also need to have the larger features so we can decrease the fabrication cost and also increase the fabrication, decrease the fabrication time. And this is where sort of this how all research came forward. Like we see a lot of designs which focus on the best performance, but can we actually make it? Can we actually fabricate it? Can we actually is this a realistic design? And this is where these two designs came up, where we put all these parameters together, and our optimizer actually found this design. So it's a combination. To come back to the question, why do we choose this? It's a combination between manufacturing constraints and the performance that we're actually looking for in into a light sail.
And so then from a manufacturing perspective, give us a sense. I mean, I think people are familiar with lithography. I mean, this kind of sounds a bit like, my father was a photographer and he had an enlarger in the darkroom, and that you would shine down your negative of the picture onto the photographic paper, and then you would develop it, and then you would have your picture, and you could make the picture bigger or smaller just by changing the height of the enlarger. So is it sort of like that you're sort of like fine tuning this process so that you get a swatch of material that comes out the other end of this?
Yes. So if you just focus on the optical lithography part, we have the luck that we have a stepper machine which you can put a big piece of glass, and that's like sort of the negative of your image. And then you flush that big piece of glass, which is onto your sample, and then you actually make a picture of that onto your sample. So our material is made out of silicon nitride. We have a wafer, we have a layer of silicon nitride, and then we put our photosensitive layer on top of it, and then we optimize it that we just photo by photo fill the whole patch with structure that we need. And then you have your lithography mask, and then the actual fabrication starts, because then you have to etch your pattern in the material, and that's where the most tricky part comes, because these machines are quite well developed, and we were able to get the pattern on quite well. But the actual struggle was in making the device and actually making it freestanding. So we actually have just a single layer of 200 nanometers with the structure on top of it.
Yeah, and I mean, I know that like in the Netherlands, you have like the greatest lithography machines in the world. Like they are the ones that are being used by TSMC and all these various chip manufacturers. You have to ship these monster machines over to Taiwan and the US and places to actually. So it's interesting that you've sort of like got the machine that can do the design for you, but then it's the underlying actual production side that no one's built the tools yet, and so it's much more of a handcrafted process to get there.
That's true, and I think this is something I didn't realize when starting my research, that we're in the Netherlands and also in the Technical University in Delft. We're really lucky with extremely good research facilities, because usually the research facilities are not blessed with the machines that we have. So that also allowed us to actually ask us these questions. What can we do in practice, and how can we improve the system? So that's actually a great blessing for the research side.
Yeah. And so, if you go back to the original requirements, or, I guess I'm sure people have done the math and said, how big do these things need to be? Like if you actually have a powerful laser and you don't want to vaporize your light sail, there's a certain amount of energy that you can be putting onto it. There's a certain size this thing has got to be. How big do you think now light sails are probably going to have to be to fulfill this mission?
So I think we need to be clear that so far nobody has actually put a laser on a piece of light sail material with the power densities that are out there. We are now currently trying to do that, to actually see what the power densities are that these materials can actually take, which is really exciting because sometimes you have feels like a shooting range in the lab where you start to explode stuff because you have to make sure that the laser actually hit it. Yeah, there's some financial action into the research, but we so far I think the moment you talk about 1 gigawatt, 10 gigawatts lasers, you really should look at least 10 square meters, 16 square meters, so 4 by 4 meters of sail, which is a really decent size if you want to make it out of the material we propose it of.
How heavy would a 4 meter sail be out of that material?
So this is, I think this is also a bit where we really go into the difference between the initial targets that has been set in the Breakthrough Starshot, where the initial goal was 1 gram, and we need to be able to illuminate it within a few minutes. So if you really want to reach this 1 gram limit, you have to go to a 500 nanometer thin material. You stamp it with holes, and that's going to be tough because that's if with this type of thickness, the whole effect of the holes actually diminishes. So you get a way less reflective, and it's much lighter, but you don't really get the reflectivity back. So there you have this balance in. So what we think is more realistic is that if you go more to the 2, 3, 4 grams, but it's still a crazy number because a dollar bill, I actually looked it up this morning, is 1 gram. So you have a sheet of material, 4 by 4 meters, covered with nanostructures, things, which are 1,000 times smaller than your hair, and then it's only allowed to weigh as much as $5 bills. It's still an insane engineering challenge.
Yeah. And I mean, like, obviously, I mean, I think people go straight to, why aren't we sending these things to Alpha Centauri? Like, that's the goal. But the reality is okay, fine. It's 16 square meters and it is 4 grams, and you can accelerate it to 100 meters, 100 kilometers per second, and then you can fly out to Pluto in a month.
Yeah.
Right. Like I think there's a lot of work that could be done with this within the solar system that then obviously people will, once it turns into an engineering challenge, that then you can start to shave away the weight, improve the laser, tune in that perfect reflectivity and so on.
Yeah, definitely. I think that's actually the part that almost makes me more exciting because it feels way more tangible. The going to Alpha Centauri is a feat, and I think it's a challenge we can solve. But I think we literally have the technology now to send these things into space. Because if you stay in the solar system, you don't need the 10 square meters. You can literally use a 10 centimeters wafer, like a 4-inch wafer. Then the challenge would be how you put the laser on it and how you can actually get there. But that should already be enough. And you can go way lower speeds. So you don't have the whole problem with the Doppler shift. And that makes sense.
I was going to ask you that. I see. Right. Like, the hole size that you're using for the light is changing if you're actually having like significant redshifting as your sail is going away from you.
Yeah, like that's something you have to take into account. Like, and if you go lower speeds with a decent amount of power, you can still go to Mars in 1 week or 2 weeks. It's still crazy, right? That's things we can never think about. And I think that's much more exciting if we actually think about, not necessarily more exciting, but it sort of gets me excited to see that there is also a possibility into our own solar system. That's I think insane to think that we can almost use it as postcards. You can just send postcards to Mars and get it back, and it's like you have to catch it. That's the other challenge. But
Yeah, I mean, I think about the planetary science community and their goal of imaging various asteroids, Kuiper Belt objects, maybe even long period comets and things like that. And there are millions, and each one is its own special, interesting mystery that all fits together to solve this puzzle of the formation of the solar system. And so, well, what if you could say, okay, pick 1,000 targets. We're going to send wafers to 1,000 different asteroids in this one mission. Yes, please.
Yes, definitely. And of course, it's going to be there are different challenges coming along, but I think it's an easier engineering challenge to keep it in the solar system. And the whole idea was always that you sort of spray and pray. You take one specific thing, you maybe 2, 3, and you try to point it towards the target that you want, and then you hope that you fly by, take a picture, send it back. But the technology we have, like the cost of a wafer is nothing. The cost of the fabrication, if you make it small, reduces drastically. So also from a fabrication standpoint, it makes the mission much more easier.
And so have you sort of thought about what you think would be a very feasible near-term kind of proof prototype that we could start building to use the technology to explore the solar system?
So like the proof of technology is what we're trying to do in the lab at the moment. I think
right, the blowing things up part.
Yeah, it's like the moment you so we all have this theoretically idea. We know we have radiation pressure, and we know that if you put a beam on your material, it should be pushed forward. But nobody has actually shown this. Nobody has actually shown that we can do this. And of course, if you look at the solar sails with Icarus, we actually do see that it works, but that's way lower powers. So I think for a short-term proof of concept, we really have to see, can we make maybe a wafer-sized light sail in the lab, put this laser on it, and see if we can actually push it up, see if we can levitate it. This is still really in development, but if we can do that and we can reach the power densities that we need, and we actually see a movement, then we're practically there. That will be an amazing step.
We're practically there. That's it. We're done.
Famous last words, but
yeah, exactly. Yeah, I suspect there might be, other technical issues that will rear their head as you move forward, attempting to manufacture these things in complete vacuum the entire time and set them up into an apparatus and then fire at it with a high power laser, attempting to sense any movement. Yeah, what could go wrong?
Yeah.
Do you have the laser?
Yes. So we're having a 400 watt laser, and then depending on the size we make it, we can actually reach the power densities, which are equivalent to what people envision for a light sail mission in space.
I mean, I need to do a different interview with people on the laser side of things. Do you think is the laser technology progressing at the rate that I think the Breakthrough Starshot people were hoping to see? Because I mean, there's so many applications for lasers. So
yeah. So as far as I know, yes. One of the leading experts, Philip Lubin, has this idea that you can phase lock a lot of lasers. So then you don't need to make one big laser. You can make multiple small lasers, which you can then combine to actually get to the power densities and the distance that you need. And this is a really scalable method. And as far as I know, this is a technology which is really far developed, which should actually make this possible.
And it seems like it would be useful as well. Like if you're trying to apply a smooth force across the entire surface of your sail, it makes sense to hit it all, each part at the same time with an array of lasers, as opposed to one which would sort of put too much heat and energy and force into one small part, and the rest wouldn't be getting the same kind of pressure.
Yes, exactly. That's everything you want. You want to have like a more uniform force on the sail, so the acceleration forces do not tear your thing apart. If you go too much in too high of a power density, you are maybe able to go over the limit of the material. You would burn or melt it. So in general, you always want to have as low power density as possible, so as large of a laser beam, which can actually push your sail forward.
And is there like an upper limit, do you think, where even this material is going to start to melt? Are you thinking about other materials that have a like higher capacity, or is this like the perfect material?
Um, it's a really good question. I think for now, this is the material where we see that it's the highest potential. It has parts per million optical absorption, which is barely nothing. But I think the biggest challenge here, which is a big unknown, is that we don't really understand how the absorption works for these photonic crystals. Because what we said in the beginning is that we are making a resonance of light in our sail. And we do not fully understand how that resonance actually contributes to more absorption. And this is, I think, where the limit would be, is at the moment we increase the power density and we start to try to find the limits. That's probably where we would find it.
Lucas, what are you obsessed with right now?
So at this moment, I think I'm really obsessed more with the fact that we have all this theoretical knowledge, and we are now at a day of age where we have the luxury that we can actually take this theoretical knowledge and put it into practice. And this is actually really what drives me. I don't have a physics background. I have a mechanical engineering background. So now being in nanophotonics and being in a really physics-based community really drives me, because it allows me to push the boundaries, put practical things in there. And I think this is what we need. This is in the end what we need to actually get out of the ideas and make this science fiction science and not fiction. And I think this is the main part that drives me. And I think it's also always really interesting when you talk to people or talk to people at conferences. There are always big caveats. There are always big challenges ahead. But if you go one step back and we try to solve step by step, we actually see that if we try to reach for these really big challenges like Breakthrough Starshot or trying to go to Alpha Centauri, that's where we actually start to discover new types of physics or try to solve new types of problems. For example, the things that we now make, these large-scale photonic crystals, we can only make this now because we pushed for these light sails. And then you suddenly have different applications in mind. So this is really the step forward, is trying to make science fiction reality.
I totally get that sentiment that we sort of live in these two worlds. Like on the one hand, we have science fiction that is sort of informing our future, our minds about what the future should be. And science fiction is a terrible guide for what the future will be. Like, where's our warp drive? Where's our anti-gravity, right?
Yeah.
But it gives us a goalpost, a place, a direction to go, okay, like, yeah, maybe we won't have the Enterprise, but wouldn't it be cool if we actually could send a mission to another star system? That would be incredible. And yet it feels like we then go and look at the current landscape and see chemical rockets taking off, people terrified to consider other kinds of more challenging technologies in their missions because, you know, they want their missions to be safe and stable and to return their science. And like, no, I don't want to put a Hall effect thruster into my spacecraft, right? I want to keep, I want to make sure that all of the risk profile comes down, down, down. You know, a space tested Pentium processor, please, as opposed to some, you know, quantum computer that someone is proposing that would work really well in space, maybe. And I think light sails feel like they are the very epitome of this conversation, because like I just see like people are demonstrating light sails. I mean, we've had the Light Sail 2 mission from the Planetary Society. The Japanese had their light sail mission, and NASA is working on various kind of light sails. And yet you don't see light sails just being applied to every spacecraft out there because it, you know, you got a free form of propulsion if you just put this thing on it. Makes sense. And I think there's this, it feels, I don't know, as a person who kind of watches this stuff progress, it feels like it's never going to happen. And yet people are making really interesting like developments that eventually will get us there. It's almost like it's not just an engineering thing, it's the policy side that we have to figure out to get this stuff in operation. And so I'm glad that that's the thing that you're obsessed with as well. As a, you know, as a mechanical engineer, you got to go beyond theory. You got to move into practice. Lucas, absolutely fascinating conversation. Thank you so much for taking the time to chat with me today, and good luck with the test. I can't wait to hear what happens when you try to fire lasers at vacuum formed photonic crystals.
Goodbye. It was I enjoyed it a lot. Thank you.
I hope you enjoyed that conversation with Lucas Norder. Now I'm going to give you some final thoughts, but first I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Bear Lake Roofing, Brian Bodie, Carradwin, Chuck Hawkins, Commander Baylock, Cy Nelson, David Gilton, David Matz, Dustin Cable, Evan Pearl, Greg Feely, Hans Schultz, Hudson Ward, Jay Graves, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Marcel Smits, Michael Purcell, Modzo, Paul Robach, Ren Kaidu, Robeck, Sean Sargent, Stephen Fowler-Melny, Thomas Elskadron, Vlad Chiplin, and Wolfgang Klotz, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. Obviously, this is a very exciting technology, and you know, Lucas and I didn't get a chance to really get into it, but there's a lot of other really interesting practical applications for putting photonic materials onto other spacecraft. You can imagine that these could be used as reaction wheels where you could fire a laser at your spacecraft and start to turn it. That being able to let in very specific wavelengths of light and block other wavelengths of light, there are other kinds of applications across a lot of different technology. And this is what you always seem to find is that, you know, as you develop these kinds of technologies for some big, grand, ambitious goal, not only do you move forward to that goal itself, but in fact, other applications present themselves and you realize that, oh, actually, this is maybe something else that we should be following as well. And this is how this process works. And, you know, the underlying lesson that always comes back is like, be brave, aim high. Think of big ideas, but then be practical, chop them up into little pieces, figure out how you're going to be able to accomplish this stuff and remove obstacles as you move forward and as all of human understanding of the cosmos continues. So I always find this very fascinating. Another interesting interview. I hope you enjoyed it, and we'll see you next time.